Oh, yeah, that is the key, yes. All right, let's take a look at a couple of things here and talk about some things, and then we'll get into our homework. Let's maybe have you jot down a few things here as we kind of talk about where we're headed with the quiz. I've been kind of struggling with when I want to do this quiz and how much to cover, whatever. So I think the Monday quiz is just not my favorite thing to do. So what I decided to do is we're going to add section 2.4 into this a little bit and do that as our quiz and probably have it on Tuesday. So just looking ahead with Thanksgiving coming up and what we want to get to, maybe hopefully before Thanksgiving, will be this is how we'll do this. Okay, so and that'll give us a little more time to review some of this algebra stuff and so forth as well. All right, so let's just kind of organize our thoughts a little bit here on what it is we've been doing, because this whole chapter is a little disjointed. There's several things here, some of them seemingly unrelated, that you have to kind of keep track of, and so that's kind of what's maybe difficult about it a little bit. So if we're going to look at sections 2.1 to 2.4, starting with 2.1, and this is just kind of a general overview of kind of the important ideas here, not a complete list of everything that you have to know, obviously, but just kind of overall concept. This is when we first learned about, the definition of the derivative, f prime of a. And we literally took that slope at a point into an actual formula where we could actually find the value. So instead of having to estimate two close points, which we still might be asked to do, you still might be asked to do slope at two close points. If you have a table of values, if that's all you got, that's all you can do to estimate the slope. But we found a way that we could actually find it. We could say, hey, we can see what the slope is. Those 2 points get really, really close. As h goes to 0, then we can see what's happening. Okay? But then also what we were working on today is this idea of a limit. And that's kind of a little bit of a side trip, but the idea is, hey, if this is one of the most important definitions we do all year, and to be honest, integrals is the same thing. I mean, limit is probably the single most important idea that makes all of calculus happen. So we probably should spend a little time on it, right? I mean, if you think about how we did limits on the areas, remember the area when we put the rectangles underneath the area? And we said if you do 20 rectangles, it gives you a pretty good estimate. Well, if 20 is good, 50 would be better, and 1,000 would be even better, right? Well, how many would really be good? An infinite number, right? And so that's a limit. So the area under some weird curve is actually the limit of the areas of an infinite number of rectangles. So that's a limit also. So the two main ideas of calculus, slope and the area, both involve limits. So we really need to understand this concept of limits. So here's the first time we've seen it, so that's why we're spending some time doing these limit problems, all right, which seem to be kind of unrelated to the whole slope and derivative stuff. And they are, in a sense. But we do use them, we do use them in these important derivative and calculus things, and so we need to understand it. All right, but essentially that's where we work some stuff out the long way. And you might think of this worksheet that you just got done doing as more of doing stuff the long way. The algebraic way is really what it is. It's working them out using algebra to find these limits. Okay? And we'll talk some more about that here in a minute. All right, then section 2.2 is basically where we learned about these shortcuts. All right, we used the definition of the derivative in 2.1 to learn this power rule shortcut is basically what we learned there. All right? And, of course, we also learned how that works for square root, like x to the 1/2 power. We can bring the 1/2 down in front, or a negative power, it still works. And we talked about shifting and stretching graphs and being able to do that and how that affects this. Okay, so there won't be a lot of that on there, but there will be some. And today we're going to actually, we're going to go into section 4 a little bit today, and we're going to learn how we can do some chart stuff using that derivative shortcut. All right, and connect it back to chapter 1. All right, so there'll be a little bit of that on a quiz where you have to maybe do some of these shortcuts. Okay. 2.3. Now I got a lot of stuff here, so let's go through it starting on the left over here. Okay? This stuff up here on the right-hand corner we'll come back to here in a minute. All right, so section 2.3 now is this kind of this side trip we took into investigating limits. So one way to do limits is algebraically, which you attempted on that worksheet today. Most well,
so much faith.
that's right. Well, I did come around and look at them, so but anyway, they were pretty good attempts. All right, so algebraically, now there's three algebra things that you need to be able to do. Well, actually four, and I kind of wrote them out of order here. Substitution is probably the one you want to put down first. So go ahead and write down substitution. I put that one last because I kind of forgot about it. Substitution is the first thing you ought to do. You ought to, if you want to do the limit as x approaches 2, then you ought to take a 2 and plug it in. Okay? You ought to take a 2 and plug it in. Now, all right, so, top seat. So, substitution. Now, over here on the right, I wrote down some stuff about substitution. Okay, so what could happen? So on a limit problem, like on your worksheet, you do substitution, all right, and you say as x approaches 2, so you plug in a 2. What could happen? Well, the first thing that could happen is you just get a number, right? So you just get a number like this problem. I just wrote down a real simple one. So limit as x approaches 2, right? We should have a whole page of these on the quiz, right? You plug a 2 in, the answer is 5. You just get a number, right? And that's your answer. Unless it's some really weird function, then something else might be going on, but it'd be easy to record, like a piecewise or something like that, right? And we actually had one of those in the homework in the book. We'll talk about that. But just a very simple one like that. Plug in a 2, you get 5. There's your answer. So if you get a number, you just stop and you're done. All right. And what happens most of the time is you get 0 divided by 0. That's what happens most of the time in these limit problems, because those are the most interesting ones to deal with. All right. Now, I threw in the word indeterminate there. Indeterminate means cannot be determined. And then that's what that means. When you're doing a limit problem, you get 0 over 0. Of course, that's undefined. But what that means is we cannot determine if there's a limit. There might be. Usually, 0 over 0 is a hole in the graph. And like we saw in the video yesterday, the two cars can still meet at a hole. So the limit still might be there. So we still have to do more. So that's why I said keep going. If you get 0 over 0, keep going. That's when you start doing conjugate and all that stuff, which we'll put up here in a second. Okay? So if you get 0 over 0, there might be a limit. You keep going. I think that happened on the worksheet a lot today, didn't it? Okay? The other thing that can happen is you get a number over 0, like 6 over 0, negative 2 over 0, something like that. For right now, that's basically a vertical asymptote in the graph. If you get that, we'll just put does not exist. And if we're doing a no calculator algebra one, we'll just say does not exist and stop there. And I think there was one on the homework where you got 0 over 0. Was it number 3? You plugged in first and got 0 over 0. Now, some of you actually might not have even plugged in first. Some of you, I think, got so excited about factoring that you did that right away, right? If it's possible to get excited about factoring. But you got in a hurry to factor, okay? Yeah, it's great. I mean, I do, but that's me. So on number 3, if you plugged in right away, substitute right away, you get 0 divided by 0. So then you keep going. So you factor them out, canceled, then you plugged back in, and you got 12 over 0, I think, right? Well, that's when you say, oh, okay, it does not exist. So you thought maybe it was a hole in the graph. You thought 0 over 0 was going to give you an answer, but then after you factored and canceled, it was 12 over 0. Oh, you say does not exist. That's when you can stop right there. Okay? And then I guess the one I didn't say is what if you get 0 over a number? What if you get 0 over 5? That's 0, right? That's number 1. That's just a number. So if you get 0 over 5, that's 0, and that's your answer. Okay, so that's number 1. So those are really the things that can happen when you get substitution. All right, so now, So you try substitution. All right. And so substitution gives you 0 over 0. So what can you do? Well, one option is factor and cancel. So that happened on some of the worksheet ones today. Okay? Factor and cancel. Now the cancel is a key part of that. That's the whole key to doing them algebraically. You got the h's you want to cancel over the x's or the x minus 2's or whatever. Something needs to cancel so that you can do the limit. Then you substitute in. All right? The other thing we said to do is common denominator. And I threw on the word cancel. Because again, I want to keep reminding you, several people that came and asked me about these did the common denominator, and but they were like, but then what? You got so hung up in the algebra part of it, you kind of forgot what you were trying to do. You're trying to get something to cancel. Because the whole reason you're doing common denominators is you've got 0 divided by 0. So you want something to cancel so that won't be there anymore. All right, and then the other one is that conjugate method. So we want to do the conjugate method and cancel. The whole point of doing the conjugate method is so something cancels. Okay, those 3 algebra techniques you need to be able to do. I'm not saying you'll have to do all 3 of them on the quiz, but any one of those or 2 of them or whatever could be on them. Okay, so you need to know those. All right, so that was our focus today. All right, on today's homework was this algebra component of it. And what we did earlier with the long way on those derivatives was the algebra way of doing limits. Okay? Today we're going to do some more like I did yesterday where I showed you the table on your calculator. So we're going to do a worksheet with some calculator tables. We're going to graph them on our calculator, do the tables, copy down the tables on our paper, and visually see the limit numerically based on table values. Okay, so we'll talk more about that here in a little bit. And then the last one is do limits with graphs. Okay, and that was your book homework today. Okay, your book homework was here's a graph, and then I ask you some limit questions off of that. And that's where you envision the cars meeting, right? And if they meet, there's a limit. If they don't meet, the limit doesn't exist. And then we can talk about the limit from the left and the limit from the right and stuff like that. All right? So that's kind of a summary of what we need to be able to do with limits. And then the other new thing we'll do today is what Section 2.4 is about. Now, Section 2.4, what I'll tell you so far, and there's another thing we'll talk about in a little bit, is how can we take what we learned on the chart stuff in Chapter 1, that big quiz we just got to take, and many of you did very, very well on. And how can we do the chart stuff with equations? We did the chart stuff with graphs. Now how can we do it with equations, like local max, local min, inflection, stationary points, increasing, decreasing, stuff like that. We won't get into inflection points and that concavity just yet, because that involves a second derivative. So we'll probably just deal with this for right now. And so we'll do a problem like that today, and you'll have a little bit of that on your homework for tomorrow. Okay? And I'll try it should get some work time, and try not to keep the homework fairly short, so that you can go back. Some of you, I think, still need some practice with some of the algebra. Go back and do some of the long way, some of the stuff from before, and kind of try to stay sharp on that and see what you need to come get help with, if anything. All right, so let's go to the worksheet. Not that one. I think we could do that one. Yeah. All right. So and I apologize for not having the answer sheet. I thought I had it, and then all of a sudden this morning I couldn't for life of me find it. And I haven't had time today to make a new one. So we'll just have to go by democratic vote. Okay. So number. Yeah, that's right. Number 1. What do you got? Negative 3/4? Yeah. I thought I remember hearing. Okay, again, you plug in, you get 0 over 0. So you factor, cancel, you get negative 3/4. Okay, on this one, now here some people, well, no, not this one, the one I'm thinking. Here you get negative 2 divided by 0. Right? Right off the bat, or when you cancel? Right off the bat. You get negative 2 over 0. Now, some people went ahead and factored, canceled, and then got 1 over 0. That's okay. That's okay if you did that. You end up at the same place. It does not exist, right? Like we were just showing on the thing up there. If you get negative 1 over 0 or 1 over 0 or something like that, it does not exist. Okay, somebody in their class asked, was it wrong if I went ahead and factored and canceled? No, because you're going to end the same place. You're going to end the same place. Does not exist. Okay, but you should substitute first. Okay, here's the one we talked about. You get 0 over 0 when you substitute a 5 in. Maybe you skipped over that and just factored right away. You got 12 over 0. Does not exist. And you can stop right there. Now later on, and sometimes on does not exist, like in the book, you do have to do more. You have to talk about the one-sided limit from the left and the right, but not on these algebra ones right now. Okay, here you plug in a 2 on this one right away. I mean, again, some of you might have factored and canceled, but you don't have to. You can plug in a 2 right away, and you get 20 over 4, which is 5. If you factored and canceled, you still get 5. Okay, so you get a number, you just stop. That's your answer. Okay, so I want to do one of these conjugate ones, and so I'll just I'll do 5, and I'll just get you started on 6. The conjugate would be radical. This is radical minus radical. So what you're going to want to do is take radical plus radical times the top and the bottom. Okay, and what should happen is some nice things down here. The radicals will go away. The 12s should disappear. You'll end up with x squared down here and x squared up here, and those will cancel. And once those x squareds and all that happens, you end up with like 2 radical 12. Okay, which you could simplify that. I'm okay if you leave it at that. Now, let's do this one, and then once you go through the mechanics of that, you'll see. Now, keep in mind, you should FOIL out the bottom, the conjugate one, because that, the radicals disappear. Up here, you should not distribute that x squared through there. Again, your whole point is to cancel. Okay, the whole point is to cancel them. So you want to leave that factored up on top, so something will cancel. Now, in this one, it's on the bottom, and so we're going to do this. It's the radical is what we want to always do the conjugate with in these problems, okay? It's not top or bottom, it's wherever the radical is. Okay, that's the one we're trying to do. So here's what you want to multiply by. Now on top, I just want to leave that. Okay, again, I saw some people foiling that out, and that's not what you want to do because we're trying to cancel things. The bottom we do want to FOIL because that's why we did the conjugate. The outers and inners drop out, and we end up with x minus 9. Okay? Well, these almost cancel, but what do you need to do? You got to take out a -1 because when you take out a -1, the 9 will turn negative, the negative x will turn positive, so you'll end up being x minus 9. Now we can cancel them. So, and remember, once we cancel, the whole point was to get something to cancel. Now we can take that 9 and we can put it in for the x. So we got a negative, and then we got radical x plus 3. So we put the 9 in, square root of 9 is 3, 3 plus 3 is 6, stick on the negative, and we get -6. Okay? All right. See, on this one, when you do the conjugate down here, and I said I wasn't going to do it, but what the hell. Right? When you do the conjugate down here, this radical times that radical is x squared plus 12. That times that is 12. Those 12s will go away. So the whole bottom will just be x squared. And up here, you've got this x squared. So that x squared can cancel that x squared. So all you're left with is that, which is x squared plus 12 plus radical 12. Well, now when you put your 0 in for x right there, you get radical 12 plus radical 12, which is 2. Okay, so that's what happens with that. Number 8 down here, you're simply, this is like one we did, this is just like ones we did the long way back in section 2.1. You're just going to have to FOIL this all the way out. You FOIL this all the way out, and the 8s will 0 out. Then you can factor out an x to get the x's to cancel. That's just like making the h's cancel. It's the same thing. And what was the answer on 8? 12. Okay? All right, last comment or thing that I'll help you with would be this one. Now, the way this one's written, the method that I was showing you is a little harder to think about. I was showing you about clearing out fractions. Well, that's when you have a fraction on top of, a fraction within a fraction. And we don't really have that here. Now, we could have it if you put all this over a 1, right? And then just do 3 times that quantity, and then on the bottom have x, right? X times 1, put that on the bottom, and then 3 times this quantity. And then you could clear out the denominator like I'd been showing. But a lot of you might not have thought to do that. So the bow tie method is pretty good here. Or the just get a common denominator. It ends up being the same. So you would take this top and bottom. If you're doing the common denominator technique, you just do this, and you would just do this, 5 minus x. Now, I was showing a few people this. It's really no more than doing this, guys. 1/3 minus 1/4. What's your common denominator? 12. 3 times 4, right? Well, how do you get a 12? Well, you take this one times 4, top and bottom. You take this one times 3, top and bottom. And that's all I'm doing. The common denominator is this times this. So this one I need to do that. This one I need to do that. Now, it's really the same as bow tie in the end. See, on top, you're going to get 5 minus x minus 5 plus x. And your bottom is going to be your common denominator. 5 minus x, 5 plus x. Right? And then, of course, you still have that 3 over x kind of hanging out there, not doing anything, just kind of rooting around. Okay? That's basically your common denominator right there. And now you just distribute. So what happens up here? The 5s are going to subtract out. And what do you have left? Negative 2x, right? So the 5 subtract out, you have negative x minus x, you just have negative 2x up there. Now what? And this is the part a lot of you weren't seeing. I saw several people get to this point and they're like, now what? Well, common denominator and cancel, right? The whole point was to try to get something to cancel, because remember, let me back up 1 second here. I kind of skipped over this. I skipped over substitution, right? I said you should always substitute first. If I put a 0 in for x, we get 3 over 0. And then put a 0 in for that x, I get 1/5 minus 1/5, which is 0. So I get that. Is that 0 over 0? Actually, it is, right? Because if this is 0 over 1, right, you just multiply. So that is 0 over 0, okay? So I kind of glossed over it because we haven't really seen one that's like that. But technically, that is 0 over 0. So we keep going here, but we're trying to get those to go away. Well, that's the secret right there, is the cancel. That's what I was hoping would happen. Because now I can plug in my 0. So on top I have 3 times negative 2. And on the bottom I put in my 0. I got 5 times 5. And there's my answer. Okay? So, I'll give you some problems where you can practice just getting common denominators, and practice getting doing the conjugate thing maybe tomorrow with some practice on that. All right, let's go ahead and go to our book problems. And people watching the video, I apologize. Oops. You're not able to see this right now, but we're on page 110, and we'll just run through these answers. All right, so we're looking at one like this. We're thinking about the cars, do they meet, and that kind of thing. So I'll just run through these. Stop me, though. Please stop me if you've got a concern about something. So the first one is x approaches 0. So as the cars come in, they're going to meet right there at 2. That's always the y value we're interested in, so at 2. As x approaches negative 3, right here, the cars meet down here at negative 1. We don't even care about this dot up here. We just care what's approaching, negative 1. Next one, as x approaches negative 1, well, they don't meet. So what do we say? Does not exist. Limit does not exist. Right? No limit is okay too. Does not exist. But then the direction said discuss the one-sided limits. Okay, so what that means is the car on the left is equal to 1, and the car on the right is equal to 2. And I'd want you to actually write that out. Either say it out, just write it out like that, or actually use limit notation. Okay, say the limit of f of x as x approaches negative 1 from the left. The little negative means from the left, and the little plus means from the right. Okay, so 1 on the left, 2 on the right. Limit doesn't exist. Okay, next one, 2 from the left is 1. Next one, 2 from the right is 1. Number 18, what's the limit as x approaches 2? 1, because both cars meet at 1. All right, so those three kind of went together. 19, negative 2 from the left, 0. Okay, 1 from the right, 0. Okay, negative 4 from the right, negative -4 from the right hits at -2. This is we couldn't do from the left. So we couldn't even ask the question, what's the limit as x approaches -4? Because you got to be able to see on both sides, right? So we wouldn't even, I mean, it's not a trick question. I wouldn't ask you that, okay? We can only ask -4 from the right. 4 from the left. -1. Okay? Then we get into these f prime ones. Well, f prime is slope. So remember, we're always talking about the y value. The y value of f prime is slope. So when they ask me for x approaches 3, I just got to look at the slope. So what's the slope from the left? -1. What's the slope from the right? What's the slope from the right? Still -1. This line is slope -1. Doesn't matter what, usually we always say from left to right. Well, this is one exception when we always do left to right. But from the right, this still has a slope of -1, right? I don't care that we're going uphill as we go on there. This line has a slope of -1. So the answer is -1. Okay? From the left, from the right, f prime is -1. 24, -1 from the right. 0. That slope is 0. 25, -1 from the left. Slope is 1. So, they didn't ask, but at -1, the limit would not exist, right? Because the slope on this side is 1, slope on this side is 0, okay? So, at -1, the f limit did not exist, but so would the f prime limit not exist. Okay, where are we at? 26? -3. From both sides, the slope is 1. Okay, was that it? We stop there? Oh yeah, 39 through 42. Okay, now, on 39 through 42. Okay, right here. Now, you did not have to graph this, and you could have graphed it on your graphing calculators. However, this question could very well be asked on a no calculator thing, all right? And this piecewise function, we're going to talk tomorrow about continuity, continuous functions, and get into some specifics about that. And a lot of times these are asked about piecewise functions. Very popular question on the AP test about to use piecewise functions to talk about continuous functions. In other words, are there gaps or breaks? Well, that's very interesting to us right now too, right? If there's a break in the graph, there's no limit. So we're kind of curious about that on these problems. So if we look at 39 here, x approaches 3. Well, just imagine, without graphing and without even putting in your calculator, you should be able to imagine what's going on here. What kind of graph is this first one? Parabola, upside down, right? Now, that upside down parabola only goes until x is 2, right? And it doesn't include 2, so there'll be an open circle there. And then what's this? A line. So after 2, it becomes a line. So we got part of a parabola, then switching to a line. Okay, now the thing that should be going around your mind is there a gap there, though? Does the parabola here and then the line take off from a different spot, or does it take off right from that same spot? We'll answer that in a minute. But here we want to know as x approaches 3. Which graph are we on when x is 3? We're on the line. Well, if you're on the line, what are the cars doing? Are they meeting? Sure. Where at? At whatever that point is when you plug in a 3, right? So all you have to do is plug in a 3. 3 times 3 is 9. 9 minus 5 is 4. Limit's 4. Because on the line, when you're at 3, you're on the line. And those cars, as they come into 3, will be right on the line. At that, whatever that y value is, that's where they'll be. So you just put in a 3, so you get 4. Okay? What about 0? What graph are you on when x is 0? You're on the parabola, right? So when x is 0, you're on the parabola. The car's going to meet on a parabola? Sure, they're going to meet whatever that y value is. So you just put in a 0. 0 divided by 2 is 0. 3 minus 0 is 3. So the answer is 3. Skip this one. Let's go down to this one. When x is 1. We're also on the parabola, right? So on the parabola, the cars will be meeting at whatever the y value is. So we plug in a 1. 3 minus a half is 2.5. So they're going to meet at 2.5. Okay? The interesting question, though, and whenever you look at a piecewise function, you always want to look over here because that's where something weird could be happening. The other places, nothing strange is happening. It's just a parabola and a line. But where the one ends and the other takes off is what we really care about. So how can we tell if there's a break or not? Put 2 into both of them. Put 2 into both of them. Okay? So we put a 2 in here. 2 squared is 4. 4 divided by 2 is 2. 3 minus 2 is 1. So the parabola is sitting there at 2, 1. What about the line? Also, 6 minus 5 is 1. So what's that mean? Break? No break.
No break.
No break. That means the parabola comes in at the point 2,1, and then the line takes off from the point 2,1. Okay? So what's the limit?
1.
That y value, which is 1. So the cars will come in from both sides, one on the line, one on the parabola, and they'll come in and they'll meet at 1. So the limit is 1. So you can just imagine that, visualize that, sketch it without knowing what it looks like exactly, but you should be able to look at that and tell it's a parabola. You should be able to look at that and tell it's a line. You should be able to tell that they're meeting at 2. You should be able to do all that stuff without having to graph it on your calculator, without really having to know. You can plug in values, okay? So I think I like just doing it that way. Now, if this happened to be a calculator problem and I gave you that, then yeah, you could graph them if you wanted to. Okay? All right. So let's move onward from limits for a little while. And we did the worksheet. We did those. Okay. So what we want to do now is talk about this 2.4 stuff a little bit. Okay, I feel like I'm missing something here. Did the worksheet, did the limits. Okay, no, I think we're good. All right, so kind of a change of pace here a little bit then. So we got this thing with limits. I really think when you got all these different things, I kind of like to hit one for a while and then go on to something else or whatever. And so then we come back to it again and kind of keep spiraling back. And so it kind of soaks in a little bit. I think if you do one and you do it for 2 days straight, but then you don't do it for 3 or 4 days, and then you have a quiz, I'm not sure that's a great way to do it. So kind of seems like we're shifting gears a lot with some of this stuff, and we are, but you know, every time we spiral back to it, hopefully it becomes a little better, a little better. So we're looking at section 2.4, chart stuff with equations. So if we pull up the chart, all right, I want to talk about notation here just a little bit, and then we'll get into a problem using an equation. So we've got the chart, and I'm not sure any of this you need to really write down. It's pretty simple. This first part here. You know, when I made my chart, I didn't label the left-hand side, and there was a reason for that. Oops. So typically when we looked at these, we said, okay, this is F, and this is F prime, and this is F double prime. And so as we go down, you know, we're doing the derivative. So we start with the function F, we do the derivative, we tack on a prime, do the derivative again, tack on a prime, and we keep going. Triple prime, you know, and so forth. First derivative, second derivative, and on and on. But what we never did talk about is what if you went the other way? What if you went, well, and another one we talked about, another relationship like that was position, velocity, acceleration, right? As you go down, you're taking the derivative, right? So P prime would be the same as V. And A would be the same as V prime, which would be the same as P double prime, right? So as you go down, you're doing the derivative. Position, derivative, that's velocity, derivative, that's acceleration. So that's a relationship we always want to keep in the back of our mind and be able to use. Now, but the question then becomes, what if you go the other direction? What do we call that? Well, it's actually fairly simple. We call that the antiderivative. That's the term, the antiderivative. Okay? Now, we're gonna do some more with this over the next several days. But it's simply the process in reverse. But what you would say is the antiderivative of F double prime is F prime. Just going up the chain. You take away a prime when you do the antiderivative. So antiderivative of F double prime is F prime. The antiderivative of F prime is F. But then the dilemma is there an antiderivative of F? Sorry to say, yes there is. Any function, aside from a few kind of weird, crazy things, any function does have an antiderivative. So whatever you call it, we need to have some notation. Okay? So if I've got some function, for whatever problem. You know how it is. I could call it F, I call it F prime, F double prime. Right on the quiz, you had to pay real attention. Here's a graph. What is it? Is it F? Is it F prime? What is it? Okay. So if I've got a function, if it's F double prime, antiderivative of that's F prime, antiderivative of that's F. So what we do, and I thought of some of you as I was grading those quizzes last time, because we had a lot of questions about F and F prime and so forth. And a lot of your F's looked like capital F's. They were kind of a borderline. Couldn't really tell if it was a capital F or little f. Well, it didn't really matter in that quiz. Well, from now on, it does kind of matter, because that is what we use for the antiderivative. It's big F. So the antiderivative of little f is big F. Now, what's the antiderivative of big F? Bigger F.
Bigger.
You know, no, we just won't have one. We never ask you that. Okay, yeah, we won't ask you for the antiderivative of big F. Okay, so but what it allows us to do is start with a function, because we usually use lowercase. So if we start with a function, we can do its derivatives, and we can always go one level up as an antiderivative using the capital letter. So you want to be careful in using a capital letter, because it is going to have meaning for us from now on. So what I'll try to do is, if I just talk about F, I'm talking about little f. I don't want to have to say little f all the time. Okay, so if we're talking about F, we're talking about little f. If we're talking about capital, we'll say big F or little capital F or whatever. Big F probably is what I'll say. So big F. Okay, so this is F. But what that means is then like big F prime, right? Kind of like P prime is the same as V, right? Big F prime is the same as little f. Big F prime is the same as little f. All right? So when you see that in a problem, big F prime, those are equal. Those are the same thing. Big F prime is the same as little f. So in my chart now, since the big F there didn't have a place to be, so sometimes the chart, if the problems are talking about big F, this could be then the big F row. Since this would be big F prime, that's the same as little f. And then this would be big F double prime, but that would be the same as F prime. Okay? So we just want to understand that connection and how they go. Yes? That's right. It could be anything in that order as far as the chart goes. Right, because it's still a function. This is still the line for a function. This is the line for its derivative, and this is the line for its second derivative, right? So it just depends what function you're starting with. That's right. So what's going to happen on the homework, and it should be fairly simple other than just this new notation, but in other words, and we did talk about this. Remember, we said if I give you an F double prime graph and ask you questions about F prime, isn't that the same as if I gave you F prime and asked you a question about F, right? It's the same thing. Well, that's what's going to happen here. What if I give you a graph of little f and ask you about big F? That's the same thing, right? It's the same exact question. And that's what's going to happen to you on the homework. On some of the homework problems, they're going to give you a graph of little f, and they're going to ask you some of these chart kind of questions that you guys just got done nailing on the last quiz. Okay? So they're going to give you a little f graph, and they're going to ask you questions about big F. So really, that's the same stuff. It's just the same stuff. So answer it the same way you did before. Okay? Where's it increasing? Where's it decreasing? Where's the local max? Where's inflection points? You know, that kind of stuff. Yes?
What would the units of the antiderivative look like compared to the units of F?
Well, that's a great question. It's the same thing, but sometimes they don't have meaning, right? So we talk about why don't we go to a third derivative or fourth derivative? A lot of times those units don't have meaning. So when up here I have position, velocity, acceleration. Well, what's the antiderivative position? Well, it would be, if this was miles, let's say it was miles per hour, miles per hour per hour. The antiderivative of miles would be miles hours. Miles times hours. That wouldn't have any meaning. Now, but there are some units where that does have meaning, like in electricity, kilowatt hours. Right? So if you had a kilowatt graph, did the antiderivative of that, that'd be kilowatt hours, and that actually does have meaning. So sometimes it does. So it would just be in reverse, right? Every time we go miles per hour per hour, we always divide by the x units, the t units. Well, when you go the other way, you're multiplying by those units is basically what's happening. Okay, because it is everything in reverse. And then the last thing I'll say about it, this isn't going to be on today's homework, but we'll talk about tomorrow a little bit, is the power rule would work in reverse, right? When you do the derivative, you bring the power down in front, decrease the power by 1, right? If you're doing the antiderivative, you're just going to do that in reverse. It makes sense that you should be able to do that, okay? We won't do any of those today, but we'll practice a few of those tomorrow. So that's the concept of antiderivative, okay? Just kind of going in reverse. All right, last thing to do, and then we will hopefully should have plenty of some work time we can do. So I'd like you to turn to page 121. That's in section 2.4, and we're going to do number 19. And your homework, in your homework, you're going to have one very similar to this. Oh, now I remember what I forgot to do. Okay, well, we'll do it after this.
Unless you forget again.
Unless I forget.
Maybe you should write it down.
But
Maybe you should tell
No.
us what we're gonna do.
calculator limits,
Calculate.
calculator table.
Okay.
We're going to do it.
I was
Okay.
wondering when we were gonna do
That's the other part of the homework. Yeah. All right. So, and that's okay. It doesn't really matter what it is. So this is number 19 on page 121. This is chart stuff. So if you read the question, they give you a function f, and that is what is it? X cubed plus 5. All right. So they give us a function, and they ask us where f is increasing, where f is decreasing, where x has f has a local max, and where it has a local min. That's chart stuff, right? That's all stuff right up the chart. All right. Now, we've never done one of these with an equation before. Now, it would be helpful if we kind of know what this f graph looks like. This would be a no calculator problem right now. We're doing this as a no calculator problem. And this is a very common one on the AP test, the chart stuff, I told you that before, chart stuff is just really important for the whole class. So being able to do them with these equations is a very important kind of problem. And they have very specific things they're looking for when they do these problems. So this is a problem we're going to do a very specific way and justify our answers. So where's it increasing, where's it decreasing, where's that local max, where's that local min? Now hopefully we all kind of know what an x cubed graph looks like, especially with a positive power. It could have at most one local max, one local min. Now it could just keep going, it could just kind of bend a little, do that. It could not have one at all. There might not be any local max or min. It might always be increasing, whatever. Okay, so we already kind of know what we're looking for here. All right, so that'd be good to have that in mind. But if we think to the chart and think back to what we learned in chapter 1, think back to what we learned in chapter 1 about where's a function increasing? When f prime is positive. Now normally in those problems, we had an f prime graph to look at, right? And we had and so just let me put up an example here. So normally we would have had an f prime graph, and maybe it did something like this, whatever, right? And what did we do? Well, we saw that it was negative, and then it was positive, and then it was negative, and then it was positive, right? And didn't that little picture right there tell me a ton? I mean, think about it. That told me everything I need. Does that tell me local max min? Tells me where where f is increasing, where f is decreasing. Tells me everything. And when you have an f prime graph like this, where's the first place you look? Right there. Right there. Right there. The first place you look is when f prime is 0, right? So we got to think back to how we did these graphically. Now, they were pretty easy with a graph. That's why I like the fact this book starts with it. Most books don't. I like how this book does them with graphs. So let's think about how we did that. We looked where f prime was 0, and then we wanted to know where it was negative, positive. Once we had that, man, we had everything. All right, so it'd sure be nice if we could have this. Well, we don't. All we have is this. Can we figure out what f prime is?
Mm-hmm.
Do we have some shortcuts we learned to do that? Sure. So what is f prime? So x squared, 6x, and then 0, right? Now that's f prime. Now I don't know what that graph looks like. Now this happens to be one that's a parabola, so we can kind of get a guess at what it looks like, but we actually don't even have to, because sometimes we'll have equations we'd have no idea what the graph looks like, so we won't worry about it. But keep this in mind. What we'd like to know, the first thing you guys told me, when you had an f prime graph, the first thing you did was look at the x-axis, where it was 0. So if I have an f prime equation, what should we do? Not plug in 0, set it equal to 0. See where it's 0. That'd be just like circling those dots that I did right there. Setting the equation equal to 0 would be the equivalent of finding those stationary points. Matter of fact, many times this year you'll hear me say, hey, if you don't know what to do the derivative and set it equal to 0. Because a lot of good stuff happens from that point on. So we do the derivative, set it equal to 0. So now we got to be able to solve this. So what should we do? I usually don't do much dividing. I would do the factoring. I think factoring is safer. But yeah, we could certainly divide by 3 would be fine. But I'll just stick with factoring. Okay? Then what? I think we're solved, right? X is either 0 or 2. Now a lot of times I'll label those things. Those are my stationary points. That's what I just found, right? A little different way of looking at it from an equation perspective. Not quite as easy as from a graph perspective, okay? But we're trying to get that same information that we had over here in this graph. So far I've got this information. I know where these are, okay? Now, how do I find the positive, negative parts? How do I know where f prime is positive or negative? It was easy on a graph. Above the x-axis, below. That was easy. Well, but I mean, how do I mean, again, I'm coming back to this. How can I find when f prime's negative or f prime's positive? This is f prime, remember? Couldn't I just plug in some points in between 0 and 2, right? Plug in some points in the interval in between and see. Just plug them in and see if I get out positive and negatives. Now, there's a nice way to organize this that most calc books talk about, and it's using what I'm going to call an f prime number line. Let's organize it, and I think if you do this, okay, we're going to do an f prime number line with our stationary point. So I'm going to label it f prime, that's important, and I'm going to put a 0 on it, and I'm going to put a 2 on it. Now, I want to put hash marks there at the 0 and the 2, because those are my key points right there. And now, like Spencer said, I just want to pick some points in those subintervals. Right? And now don't put hash marks at those numbers, because then it just gets all confusing. Okay? You just put hash marks at the 0 and the 2, and then put in some numbers in the subintervals. And we plug them into where? Into the f prime graph, right? That's key. That's why I always like to label it. We want to know if f prime is positive or negative. So we put a negative. Now you can put it into the f prime here or the factored version. It doesn't matter. Might be easier to do the factored one, I don't know. -1, that'd be, now all we care about is if it's negative or positive, right? We don't care what it is, we just care if it's positive or negative. So we put a -1 in there, that's negative. -1 minus 2, that's negative. Negative times negative, positive. Put a 1 in. 3 times 1 is 3, that's positive. 1 take away 2, that's negative. Positive times negative is negative. Put a 3 in. 3 times 3 is positive. 3 minus 2 is positive. Get a positive. Okay? So what, doesn't this number line, doesn't this f prime number line tell us everything this told us? Doesn't this number line tell us exactly what this told us? Yeah, because this is f prime. This is where f prime is negative, positive, negative, positive. That's the same thing. So this tells us that f is increasing at these places. And so now let's just go answer our question. We got everything we need right here. So now let me tell you how you answer the question. So where f is increasing would be what? Negative infinity to 0, and from 2 to positive infinity, right? Just from the number line. From negative infinity to 0, and from 2 to infinity. I know it will go to infinity because I know it's never 0 again. The only way f prime if it's positive, the only way it could be negative again is if it went back to 0. And it never does, because we found the times when it was 0. So we know it will never change again from positive to negative anymore. Okay, it's decreasing from 0 to 2. Okay, now you notice I left myself kind of a gap here on C. And that was on purpose. We're supposed to do local max, right? Is that right on C? Now, the AP tests are very specific. Matter of fact, if you pulled out, we don't need to do it right now, but if you pulled out that packet I gave you at the beginning of the year, they have a whole section on the use of F prime number lines and doing local max and min and inflection points, stuff like that. Anytime you have to cross columns in the chart, which is basically for inflection points or local max min. Local max min is when F prime changes positive to negative, because then F goes increasing to decreasing. Or F double prime changes positive to negative when F changes concavity. Anytime you have to cross those columns, you have to write that out. They're very, very picky about that. So, I'm going to be too. I want you to get in the habit so by the time we get to the end of the year in the AP test, you just automatically do it. So, where's the local max? It's when x equals 0, right here. When F prime changes from positive to negative. Just like over here, when F prime changed from positive to negative, you have a local max. So, x equals 0, but here's what you have to say. F prime changes positive, and you can shortcut this, positive to negative. So F changes, increasing to decreasing. They want to know that you know that a local max is caused by that connection between F prime and F. Having the sign chart, it used to be 7 years ago, if you had a sign chart and then you did your positive to negative, or you did your local max, they kind of would count that. But what they were thinking is they wanted the people to communicate that they understand the connection between F prime and F prime. So they want you to do that. And so you do the same thing for the local min. So on D, the local min's at 2, and that's since F prime changes negative to positive, F changes decreasing to increasing. They want to see that you can connect F prime to F. Now, I think we've done a great job of that on this, on chapter 1. You guys did a great job of that. I didn't make you write it out there, in chapter 1, but from here on out, we're going to do that. Okay? So justify, and I'll try to always remind you and say justify and stuff like that, but automatic, local max, local min, we do that. All right, that's what it looks like. That's what it looks like. And so any local max, local min problem is going to look like that. We do F prime, we set equal to 0. That's our stationary points. We put them on a number line, gives us our plus minus information, which we used to get off an F prime graph, and away you go. All right? So, I said I would show you this calculator limit thing. So go ahead and get your calculators out. So homework in the book is going to be the big F stuff, some chart stuff, and then one of the problems just like 19. We kind of mimic what we did on 19. All right? So that'll be the book stuff. And then we're going to do a worksheet here with these calculator limits. Okay, calculator limits. So, let's do, let's see. Let's do this limit right here. Trying to make one up that'll be somewhat interesting. Limit as x approaches 3 of x minus 3 over x squared minus 9. Okay? Now, we know if we were doing this algebraically, we would do what? Factor, cancel. You can probably do it in your head. What were you going to end up with? You're going to end up with 1 over x plus 3 which is going to be 1/6 as an answer, right? So if we did it algebraically, we should be getting 1/6 as our limit, all right? Now, show you something on your calculator. Again, this template button right next to the 9. If you go to the template button right next to the 9 and hit that, and right down here in the bottom row, second to last one, there's a limit. I apologize, I should have shown you this yesterday. You could have been checking your worksheet one. Okay? Not that that would have helped you be able to get any farther with the common denominator stuff, but you could have checked if you had. I didn't think of that until Dakota asked me for the answer key today. We could have just done that. All right, so you've got these different things you can put in. So limit, let's do limit. X approaches 3. Now it even has this box here if you want to do a plus or a minus. Okay, I think you have to put in a, well, I'm not sure. I don't think, well, yeah, we don't have to put anything in. If you want to do a plus, I think you put in a 1. And if you want to put a negative, you put a negative one, I think. And maybe you can just put a negative. I don't know. You can try. But it doesn't really matter. To be honest, we're not going to use this hardly yet. I mean, I'm going to show it to you. You can do it for checking answers. But, you know, it's not that interesting to just type something in and just get the answer. Well, you probably think, you guys probably, you would like it. I understand that. I mean, it's kind of, but I'm not sure it advances our knowledge of anything to be able to do that. I used to always give the example of my daughter. She's getting too old now to use that example. She was like 2nd grade. I could say, well, my daughter I could teach her in 2nd grade to type that in. And she doesn't know anything about limits. She still doesn't. She's only a freshman, but still, it's not quite the same story. All right. Anyway, we just type that in, and we hit enter. Okay, 1/6. There it is. So if we do a limit problem on a calculator part of a quiz, I'm not even interested in the answer, to be honest with you, because I know you could just type this in and just get it, right? So I don't really care about the answer. As a matter of fact, here's how I usually do these on a calculator quiz. On a calculator quiz, I usually give them to you like this. On the calculator part of the quiz, I just give you the answer. You know, I just say, okay. And then my directions are justify with a table why this is true. Okay, so this is what we're going to do on the homework worksheet. Now, on the worksheet, I didn't give the answer, so you can go ahead and give the answer too as part of what you got. So what I want to do is understand why is this limit as x approaches 3, 1/6. So we go to our calculators, and we're going to go to our graph screen. Now, if some of you followed my directions yesterday, and your table is still up, does anybody still have their table on the screen? Okay, hit Control T. Control T will just get rid of the table. Okay, and then you can go in and probably you might just want to clear the scratch pad, to be honest with you. And start over. But you can go up into F1 and delete. And now let's put in our new function. Now when you put in your new function, you do not type in limit. Okay? All we're trying to do is we're trying to graph this part of it right here. We want to graph this, and we want to see what its y values are as x approaches 3. So we're not typing in the limit part. So let's go ahead and do that. So let's go ahead and type this in. So we got x minus 3 on top, and we got x squared minus 9 on the bottom. And hit enter. Now, if you're not getting the window I have, just go into Windows, Zoom Standard. Okay, is everybody getting? Ryan, you get? Is that graph okay for you? Oh no, well you can, but we're going to have to do it on the. We're going to have. This is what you're going to be doing on your homework worksheet, so you might want to do it. Right on the floor. Right there. All right. He left his phone. So anyway, okay, so there it is. Now, what are we interested in here? We were interested when x approached 3. Now, you can't see it, but there must be a hole there, right? I mean, we didn't talk about it, but if you plugged in a 3, you get 0 divided by 0. We could check that and trace. Now, you don't have to. This is not part of the problem. But you could come in here, type in a 3. Sure enough, it's undefined. There's a hole over there. Looks like there's a vertical asymptote at -3, and there's a hole at 3. Okay? So, but what is the y values approaching? Well, you know, we talked about this with tracing. Now, again, you don't have to do this for the problem, but let me just type in a 3.0001, and sure enough, we see 0.166664 or something. Well, that's what 1/6 is 1/6 repeating. So it looks like, you know, that 1/6 seems to be what the cars would be coming together at that hole. Here's what I want you to do, though. What I want you to do is hit Control T, and that'll bring up the table. So Control T brings up the table, Control T will take away the table, all right? And then we're going to do what I did yesterday, which is we're going to set up this table. What do we got? As x approaches 3, right? So we want 3 to be the beginning of our table. So I'm going to go to Menu, Table, Edit Table Settings. Now, you don't have to do this very often because once you start working on a problem, a lot of them are the same. Okay, we're going to start our table at 3, and we're going to do our table step of 0.0001. That's usually enough if we do 3 zeros and a 1. And then you can hit Enter. Now, the only problem with this picture right now is I can't see both cars. I can't see on both sides with my table. I can see 3.01, 3.02, but I can't see before 3. So I'm just going to up arrow twice, and that puts 3 right in the middle. And this is what I want, is this right here. Okay? Now, does everybody's look like this? Okay? If not, then there's something with your decimal settings or something. So on your paper, right, on the worksheet today, you will then write a table with these 5 entries: 2.9998, 2.9999, 3, 3.0001, 3.02, and then over here 0.16667, 0.1666. Now you only have to be accurate to 3 decimal places. This is undefined, but quite honestly, what if there was a 12 right here instead of undefined? What would the limit be? Would that matter? It doesn't matter. This row doesn't even matter. The undefined, it just tells us there's a hole there. But again, it's what are the cars approaching? So even if there was a 12 there, that'd be like that situation where you had this and then a dot up there, right? It doesn't matter. That doesn't matter. What matters is what it's approaching. So do you see what I'm talking about though with the table? How you can see the 2 cars, right? You can see what the Y, this is the Y column. You can see what the Y value is approaching. On both sides, it seems to be approaching 0.166 or 167 if you want to round. That would be your answer, which of course is 1/6. All right. Now, what would the table look like? Last thing, and then I'll let you start working. What's that?
Like if like the 3.001 is like a 2, then you know they don't meet.
Okay, that's just what I was going to say. What would the table look like if the cars don't meet? Well, an easy way to do it is what if these up here were negative? And these were positive, right? It would look like on this side they're coming in at positive 1667, and on this side they're coming in at negative 166, right? Or like you said, what if this was 2 and this was, right? If this side is coming to a different number than this side, then that's when you'd have that break in the graph. And then we'd say the limit doesn't exist because the 2 cars aren't meeting. And that'll happen I think that'll happen on some that you're doing. And then there'll be some where these numbers are just getting bigger and bigger, like 40,000. On both sides. Well, what's that means happening? They're going to infinity, right? And again, that'd be it does not exist if they're going like to infinity or something. If you see that, but what I'm trying to do is get you to really understand the concept of limit, to see it in these different versions, to see it algebraically. But sometimes when you do it algebraically, you get so caught up in the algebra, you forget what you're really doing. So when you see it graphically or you see it as numbers, you have a better chance of putting that together and see what we're talking about. Okay, so when you do it algebraically, and you factor and cancel and get 1/6, I don't think you're seeing the cars. You're just getting a number. You're just getting an answer. I want you to hear, when you do it this way, you see that, oh, okay. Or on this graph, you can see, okay, they're coming in right there at 1/6. That's why the answer is 1/6. All right? Okay, so here's the worksheet. And so you got the rest of the time to work on this. And the nice thing about it is once you get your table set up, like I think on this worksheet, only one of them has x approaching 3. All the rest of them, x approaches 0. So I would do the one where x approaches 3 last, or first. And then all the rest, x approaches 0. So once you get your table set up, see, on x approaches 0, you want 0 right there. So when you edit your table, you want 0 to be at the start. But once you get the table set up for 0, you just can go over to your graph screen, type in your new equation, and your table will update automatically. And you can just keep the table up there, okay? But this is what I want to see on your paper right here, okay? 1/6 or 0.166 will be the answer, and then this table on it. All right, I'll put up the book assignment then, that stuff with the chart, and that other problem, I'll put that up on the board here in a second.
So when it says check the one-sided limits, are we supposed to evaluate the one-sided limits?
They're right here. They're right here. Yes. So, great question. So like when Dakota was saying, if this one was going to 2 and this one was going to -2, those are the one-sided limits. Yeah. This would be from the left, right? 2.998. So from the left would be -2, from the right would be +2. That's why it does not exist. Exactly. Exactly. Because it's all right there in your table. Yep, both sides are right there.